Hi, in this video we present our work titled Addressing the Challenges of Loop Detection in Agricultural Environments, recently published in the Journal of Robotics. Loop closure is a key component of localization, mapping, 3D reconstruction, and structure from motion systems. It makes use of global sensors to perceive when a system is revisiting a known location and attempts to correct drift errors that can occur when integrating measurements from other sensors. In particular, we focus on visual loop detection, which makes use of cameras and the visual information they provide of the environment to detect such cases and pass this information to the loop closure system. Our work focuses specifically on how these systems work in open field environments, such as agricultural fields. These present specific visual challenges for loop detection that have yet to be explored. Attempting to make use of conventional visual face recognition systems as loop detection methods have proven effective for these domains, as we explore in our work. These methods usually employ either learned global descriptors or create global descriptors from a set of local descriptors. We show how typical methods that have been shown to perform very well in urban or semi-structured environments cannot be consistently used in agricultural environments, as no single similarity threshold can be found to satisfy a good loop detection even when dealing with different sections of the same agricultural field. On a first glance, we could attribute this to a faulty or badly trained system that does not differentiate places correctly when applied to environments it was not trained or adjusted on. But we believe this issue arises because usually loop detection systems are tested on environments where visual features change rapidly with changes in position. These can be clearly seen when comparing an extract of the Kitty dataset, which is taken by a sensor-mounted car in the streets of a city in Germany, with an extract of the FieldSafe dataset, which was taken by a sensor-mounted tractor in the grass field of Denmark. We also remark that realizing a car in a road can be much more easily accomplished, given that the possible paths they can traverse are confined to existing roads, which are also usually very distant to one another, which creates a domain-specific benefit for localization. In comparison, vehicles in open fields have little to no restrictions on the paths they can take, which not only makes loop detection more difficult, but also usually needs much more precise localization methods to prevent issues in post-estimation. We propose a method that builds onto a loop detection system first presented by Galvez Lopez and others. Our method takes as input a pair of stereo images and computes its features on them, then performs feature matching and keeps only those features that match on both images. We then reuse code from the original method to help us look for a best candidate image. As the original method is monocular, we only perform this on the leftmost image, that is the key points for the left image. Once we have a best matching candidate, we can recover the right image and perform stereo for image key point retention, that is, we retain only key points that match on both the original pair and the new best candidate pair of stereo images. Once we have those points, we do a 3D key point triangulation only on the database stereo image. With those 3D key points, we can perform a relative post estimation via a perspective endpoint system with the left image of the new stereo pair. We test our method on the FieldSafe dataset, a dataset originally conceived for obstacle detection on agricultural fields, but that also contains 3 long trajectories filled with potential loops, making it ideal for our work. We show how our loop detection system only finds good loop detections, here shown with a cross overlaid on the trajectory, with an estimated translation error of less than a meter, represented by the color of the crosses. In particular, we quantify the detection distances and the detection distance errors for each of the sequences and see that our system can detect loops where the trajectories are closer than 1.5 meters, with a relative position error of less than 1/4 meter in average. To better showcase our contribution, we compare the loops detected by the original system and by our augmented system on a single trajectory. As can be seen, even if the original system performs geometrical checks to better filter matches, The distance from the query images to the corresponding loop detections can range all the way from 0 to over 40 meters. Without any information about this relative distance, a usual loop closure system is bound to introduce errors in the post estimate and affect related systems such as mapping or 3D reconstruction. We also perform some ablations on the number of detected key points and show that there is no real need to go beyond 2000 key points, which we use for our results, given that it only helps to restrict the distance of the detected loops and not lower the relative post-estimate error. We invite you to read our complete article in the Journal of Field Robotics or our open preprint published in arXiv via the links shown here or by scanning the QR codes shown above each link. Thanks for listening.